Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adam bin Cik Joha. Today, I would like to present to you about the introduction for the steam boiler system that our group has been done. Okay, the steam boiler system is a vital technology for household and industrial processes. It's about the system working principle, components, and applications in industries such as energy, food processing, and manufacturing. Key aspects include the division of boilers into fire tube and water tube types, their design and pressure handling capabilities, and the critical role of the components like heat exchangers, safety valve, and condensate recovery system. The importance of the system is the maintenance to ensure safety, efficiency, and longevity, emphasizing regular checks and water treatment to prevent issues like scaling and corrosion. Now, we move on to the literature review. The literature review highlights the importance of industrial process control in ensuring consistency, safety, and efficiency across industries like energy, food, and pharmaceuticals. It discusses key components such as the controllers like PID, PLC, DCS, actuators like valve and motors, sensors like temperature, pressure, flow, and also human machine interfaces HMI. This system help maintain product quality, meet regulations, reduce costs, and improve safety while also being flexible and scalable for evolving industrial needs.
For the steam boiler system, it consists of 5 components, which consists of PID controller, control valve, buffer tank that acts as a lag component, a boiler, and a pressure sensor. So on here, it shows the block diagram of how the system works. Now let's move on to mathematical model for the steam boiler system. So at first, we have to look at the control valve. Control valve is actually help to regulate the flow in the steam boiler system. So we can use mass flow rate formula to calculate and create a transfer function for the component in which this is the transfer function, which is ms over vs equals to 23.55 over s. For the boiler system, this component is a heat transfer system, so it's actually follow the Gay-Lussac law and also use the formula for heat transfer during phase change from water to steam. So this transfer function for the component is calculated, and this is the transfer function, which is 0.0005404. And lastly, for the buffer tank introduces a second order dynamic as its help to act as a second lag element due to the effect it brought to the systems. The transfer function for this component is written as here, where T1 and T2 is the time constant for the systems. After obtaining all the mathematical model for the system, the final transfer function can be written as below, in which the control valve, the boiler, and the buffer tank is combined together without taking PID controller into consideration, including with the sensor. This is how the final transfer function looks like.
Hello doctor, I am Lim Yau Sheng. I will continue to present some part of the result. So for the root locus, before we find the root locus, we need to know some of the details and information of root locus. So first, our transfer function for this system is 0.01273 over 150 s cubed plus 25 s squared plus s, which is the third order system. So in this system, we have no zeros, and by solving the equation, we can find that the poles consists of 0, negative 0.0667, and negative 0.1. Next, since we have 3 poles and no zeros, so we have 3 asymptotes, which is at 60 degrees, 180 degrees, and 300 degrees. When k equals to 0, k equals to 1, and k equals to 2 respectively. So our centroid in this system is located at negative 0.1667. The breakaway points can be found by differentiate the characteristic equation. So after differentiate the characteristic equation, we found that the breakaway point is located at negative 0.0262 and negative 0.085. For the gain at the breakaway point, since it is modulus, all will be the positive value. So the first breakaway point is located at 85.202x and the second is located at 285.205. This is the root locus graph of our system after we find the zeros, poles, centroid, asymptotes, gain at the breakaway points and breakaway points. For the stability of this system, we can determine it by Routh-Hurwitz criterion method, which state that if the system is stable, there are no change of sign in first column. So in our system, it is stable because there are no change of sign in first column. All of the value in first column are positive. Next, this is the graph of the step response system without PID of our system. So it is so that the graph is linear.
Now I'm going to present part 4.4 frequency response analysis. Both diagram without PID. The transfer function is given 0.01273 over s bracket 150 s squared plus 25s plus 1. The transfer function has a pole at s equal to 0 from s in the denominator and followed by two additional poles from the quadratic term 150 s squared plus 25s plus 1 equal to 0. So the quadratic can be solved using the quadratic formula s is equal to negative b plus minus square root b squared minus 4ac over 2a. And a is equal to 150, b is equal to 25, and c equal to 1. After substitute the value, we can get the lower cutoff frequency is equal to 0.0667 and followed by the higher cutoff frequency is equal to 0.1. However, the value of the critical frequency is equal to the multiplication of the lower and higher cutoff frequency and square root the value. After that, we can calculate the magnitude in dB using the following equation. 20 log 10 multiply 0.01273 divided by W square root 150 W squared minus 1 squared plus 25 W squared. And we substitute the value W with the lower cutoff frequency, higher cutoff frequency, and the critical frequency. We use the angle of asymptote and the pole of the transfer function to calculate the phi value. When s equal to 0, the phi pole 1 is equal to negative 90 degree, followed by s equal to negative 0.0667, and the phi value is equal to negative arctangent multiply the value of the frequency divided by 0.0667, followed by s equal to negative 0.1, and same, the phi value is equal to negative arctangent multiply the value of frequency over 0.1. Figure 4.5 is a graph of root locus with PID. Based on the transfer function that have been calculated, there's no value for zeros, but there are three poles located at 0, negative 0.0667, and negative 0.1. The root locus on the real axis exists at this point. Since there are no zero, the system demonstrates a smooth transient response. The addition of the PID control has reshaped the root locus, further enhanced the transient performance and improved stability. Now is the part 4.6 frequency response analysis with PID. 4.6.1 is a board diagram with PID. By including the PID controller into the system, the board plot shows significant differences compared to the system without PID. For the magnitude graph, the gain starts from a higher value and then exhibit a peak value of negative 19.01 dB at a frequency of 0.0667 radian per second. After this peak, the magnitude steadily decreased as the frequency increased, reflecting the expected behavior of a system with stable attenuation. For the phase digraph, the phase starts at negative 90 degree due to the pole at the origin. It remains relatively stable before showing a rapid drop as the frequency increases. The phase margin is calculated to be negative 168.69 at the frequency of 0.0667 radian per second. This indicates that the system maintains stability through the frequency range, as the phase lag does not exceed critical thresholds. Figure 4.6.2 shows the graph of Nyquist diagram with PID. From a Nyquist diagram of the closed loop system with the PID controller, we can observe that the plot crosses the real axis in an anti-clockwise direction. This indicates that the system maintains stability within the given parameter. The fact that the plot remains on the left side of the real axis without encircling the critical point (-1, 0), confirming that the system is stable under the current control setting. Additionally, the absence of any crossing of the right side of the plot suggests that the system remains stable across higher frequencies as well. First figure is the step response with PID, followed by the second graph is the step response without PID, and the third graph is the step response with P, and followed by the last is the step response with PI. First is the step response without PID controller. The rise time is 3200 seconds, and followed by the settling time 5800 seconds. The peak amplitude is 0.12 with no overshoot, so we can conclude that the system is stable but slow, responding conservative with minimal dynamic performance. Second is the PID controller. The rise time is 6.5 seconds, and followed by the settling time 48.2 seconds. The overshoot is 18.7%, and the peak amplitude is 1.15. It has a balanced speed and stability, offering the best overall system performance. Third is the proportional controller. The rise time is 3 seconds, and followed by the overshoot 88%. The settling time is 520 seconds, and the peak amplitude is 2.5. It has a prioritized speed by lead to axis overshoot and oscillating due to lack of integral and derivative control. Fourth is the proportional integral controller. The rise time is 9 seconds, followed by the settling time 500 seconds. The overshoot is 75%, and followed by the peak amplitude 1.75. It can reduce steady-state error by suffering from increased overshoot and oscillating due to the absence of derivative action. Last is the proportional derivative controller. The rise time is 6 seconds, followed by settling time 45 seconds. The overshoot is 30%, and the peak amplitude is 1.3. It can provide fast response that PI with reduced overshoot, better damping, making it ideal for applications requiring rapid response with minimal oscillations. So we can conclude that the PID controller is the best overall performance, having optimizing speed and stability. The proportional controller has fastest response but highly oscillations. The proportional integral controller is good steady-state accuracy but prone to overshoot and oscillations. Proportional derivative controller is balanced option with reduced overshoot and fast response. In conclusion, controller choice depends on the specific requirement of the application. Example, stability, speed, or reduced oscillations.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqmal Akbar and my matrix number is AD220099. Today I'm going to present the discussion part and the conclusion part. So firstly, the discussion part. How different control strategies affect system performance without a PID controller. The system is sluggish with a rest time of 3200 seconds and settling time of 5800 seconds. Adding the PID controller drastically improve this to just 6.5 seconds and 48.2 seconds with only a small 18.7% overshoot. The P, PI and PD controller each have their pros and cons. The P controller is fast but unstable, while the PI controller improves accuracy but has high overshoot. The PD controller strikes a better balance with a 6-second rest time and 30% overshoot. Overall, the PID controller offers the best combination of speed, stability and accuracy, making it ideal for more complex systems. Okay, for the last part, which is conclusion, this project explores how different control strategies impact the performance of a pressure control steam boiler system. Focusing on the PID controller, we found that the right control strategy is crucial for system efficiency and reliability. Simple controllers like P, PI and PD have that use, but they each have limitations. The P controller is fast but unstable. The PI controller improves accuracy but struggles with overshoot, and the PD controller offers a better balance but still doesn't address all challenges. The PID controller, however, stands out by combining all three components. It reduces the rest time to just 6.5 seconds and setting time to 48.2 seconds compared to 3200 and 5800 seconds without it. The frequency response analysis confirms its stability, suppressing noise and improving tension response. In conclusion, for complex systems like pressure control boiler, the PID controller is the best choice, offering faster, more precise and stable performance.